and welcome to the Spring Oscillation Lab, where the total changes in energy of a system will equal 0. What is this lab really about? Well, in step 1, we will import a video and track the video using the program tracker of an oscillating spring and mass system with given mass and L values. In step 2, we will create a generic Python code for modeling such a spring and mass system, including all the forces and energy diagrams. In step 3, we will use this model and import the observations made with the tracker video in a .csv file to be able to determine whether or not the model accurately represents the observations of the spring mass system. In step 4, we will draw conclusions, such as a system such as this, while having a delta E that is delta E equal to 0, which means that the total changes in energy, both kinetic and potential energy, will equal 0. This L length is approximately 0.7 meters, and the mass is approximately 0.402 kilograms. Now we can play the video and watch the oscillation as it moves up and down, and we can see this as a graph of Y as the periods of the oscillations go. We took the results we obtained from tracking the mass as it oscillated with the spring system. We were able to take the X and Y positions and put them into a CSV file to be later imported into our model on Python. In this lab, we are given some initial conditions such as the mass being 0.402 kilograms and the length of the stretch spring as 0.7 meters. But we still need to find the spring constant, Ks, and the L naught, which is the initial length of the spring when it's not stretched. How can we find Ks? Ks is actually equal to 4 pi squared times the mass of the system over the period squared. The period is how long it takes for one oscillation to be complete. The period known from the observations is 1.4 seconds, which gives us a spring constant of 6.83. Next, for finding L naught, we are given L as 0.7 meters, and we know that the magnitude of gravity at the rest position has to be equal to the magnitude of the spring. From this, we can determine that mg is equal to K sub s times s, or which is L minus L naught. We manipulate this equation to get the L naught equal to L plus mg over Ks, or which is approximately 0.123 meters. Now let's go into our Python code with some initializations. We can set the ball mass to be 0.402 kilograms, and also have to edit the ball position using the vector 0, negative 0.86, 0, noted from the observations in the video. Obviously, the initial time is 0, and the ball's initial velocity is 0, since this is right before it is released. So I'm inside the while loop for this. So we need to find the magnitude of the gravitational force and multiply it by the f hat vector, and find the gravitational vector. We also need to find the spring vector, and knowing that F net is equal to the gravitational force plus the spring force. We can use this to find the next ball velocity with ball.v is equal to F net times delta t, as used in plenty of previous Python codes. We can also find the next ball position. Next, we need to update where the spring is. The new L being where the ball is minus the spring's position, which will be 0. The L hat being L over the magnitude of L, and the S being the magnitude of L minus the L naught that we found earlier. Some of the energy initializations we have is the kinetic energy of the ball being 0.5 times the mass times the magnitude of the velocity squared. We also have the potential energy of gravity being the mass times gravitational force times the ball's position in the y direction. We also have the potential energy of the spring being 0.5 times the spring constant times the stretch of the spring squared. Inside the while loop, we need to constantly figure out the next k value and find the delta k of k minus k initial. We can do this for the potential energies as well, and later on sum up these energies and find that our total change in energy of this system is equal to 0, as it should be, as there is no energy being interchanged with. When we run the code, we can see the model as the blue ball as compared to the red ball, which is our actual observed movement of the mass on the spring. These values do not match up very well, indicating there's some error in my code. However, there could be other reasonings behind this. For our what does it mean, we can see the energy plots below, being the red being kinetic energy, the green being potential energy, and the yellow being the total change in energy. We know that the kinetic energy and the potential energy oscillate about the x-axis, and the total change in energy should always be equal to 0 because energy will not enter or leave the system. Thank you, and I hope you enjoyed this lab video of spring oscillation.